casting process begins with either a drawing or a sample casting provided by the customer. The casting shown in this drawing will be used throughout this video for demonstration purposes. A master pattern capturing every detail of the casting is then produced out of wood. For some patterns, a master replica of the core is also produced out of wood. Lettering and logos can also be placed directly on the master pattern. For this particular casting, the master core and the master pattern are assembled together to form a single unit. The core and pattern assembly is used to produce a mold which will allow the pattern maker to make several copies of the master. The mold can be constructed from a number of different materials including wood, fiberglass, and plastic. Each half of the mold is used to make one half of the replica patterns. These scenes show the replica halves of the pattern being fitted back into the master molds in which they were made. The two halves of the replica are an exact copy of the original master core and pattern assembly. The two halves of the replica pattern are then aligned with each other, drilled and doweled to maintain their alignment during final assembly onto the pattern board. For this particular casting, two copies of the master are made. They will be mounted on a single pattern board, yielding two castings per mold. The patterns will be mounted on this aluminum pattern board. Using half of the pattern replica as a guide, holes are drilled through the pattern board to allow for alignment of both halves of the pattern replica. Once all the dowel holes have been drilled, the pattern replica halves are all mounted directly onto the pattern board. One half of each replica is mounted on the top of the board, the other half on the bottom of the board. The feeding system, comprised of gates, risers, and runner bars, is then constructed out of wood and attached directly to the pattern board. The feeding system, also known as the gating system, creates the passageways in the sand mold for the metal to flow into the casting cavities. The core box for this casting was created by making a mold from the original master core. Shown here are the two halves of the core box and the original master core. A third part of the core box, known as the stool, is shown here. The complete core box tooling consists of the two halves of the core box and an aluminum stool. The aluminum stool has a mandrel and 4 ejector pins which aid in removing the core from the automated core machine. The tooling is attached to the core machine using vacuum technology, which allows for rapid tooling changes. The core box is closed under hydraulic pressure and raised up to the chute head where the sand is blown into the core box. A gassing plate then moves into position and gas is blown through the core under pressure. The gas acts as a catalyst to harden the resin-coated sand to produce the core. The core box opens and the stool moves out towards the operator. The ejector pins raise the core to allow for easy removal by the operator. The bonded sand core will be placed into a sand mold to produce the final casting. The production sand core is an exact replica of the original master core. The pattern is ready to be installed on a Hunter automatic molding machine. This view is of the top or cope side of the pattern. Molten metal will enter the mold through the down sprue mounted on the pattern. The bottom or drag side of the pattern contains the passageway through which the molten metal will flow to get into the casting cavities. Upon reaching the bottom of the down sprue, the metal then flows along the runner bar towards the riser. Once the riser begins to fill, the metal flows through the in-gates into the casting cavities. The riser, shown here on the cope side of the pattern, is a reservoir of extra molten metal which will feed the castings as they cool to prevent shrinkage. The pattern is placed into the automatic molding machine where it is attached to a rectangular box known as the drag flask. In this view, the drag flask has been partially rolled over so that we can see the bottom or drag side of the pattern. The drag flask will be filled with sand, which will then be compacted to form the bottom or drag half of the mold. The molding machine is ready to begin a cycle. The description of the molding cycle will begin with the drag flask on the right half of the screen. The drag flask rolls 180 degrees, is filled with sand, and then rolls back. The drag flask moves over and up to meet the cope flask, which is then filled with sand. A hydraulic ram then squeezes the sand in both the cope and the drag flask. The drag flask is then lowered away from the cope flask. The drag mold is drawn out of the drag flask, and then the drag flask returns to its home position. The cope mold is still contained within the cope flask. The drag mold, on the other hand, has already been drawn out of the drag flask. This view of the cope flask, looking up from below, shows the impressions in the sand left by the cope side of the pattern. This view of the bottom or drag half of the mold shows the impressions left in the sand by the drag side of the pattern. The operator then places 2 cores into the drag mold, one for each of the 2 castings being made in the mold. A small filter has also been placed into the mold. The filter will ensure that any impurities which may be present in the metal will not go into the castings. The cope and drag halves of the mold will now be brought together to form the finished mold. On the left half of the screen, the drag mold will rise up to meet the cope mold. The cope mold will be released from the cope flask, and the completed mold will then be lowered and ejected from the machine. While the finished mold is being assembled and pushed out of the machine, another mold is being produced. The mold is conveyed from the molding machine to an automatic mold handling system. The mold is then loaded onto the mold handling system, where a jacket is placed around the mold and a weight is placed on top of the mold. The jacket placed around the mold serves 2 purposes. The jacket prevents the cope and drag from shifting, which would cause offsets in the casting. The jacket also serves to contain the sand and prevent the hydraulic pressure of the molten metal being poured into the mold from breaking the mold apart. The weight is placed on top of the mold to prevent the cope from floating on the molten metal, which would result in metal running out between the cope and the drag. There are three main raw materials used to make ductile iron. The down sprues, runner bars, and risers, which are a byproduct of the casting process, are placed into pits and remelted. Mild scrap steel is the second major input used to make ductile iron. The third major raw material used in the production of ductile iron is a high purity iron called pig iron, which is produced in Sorel, Quebec. The raw materials are transported from the pits using an electromagnet. The raw materials are placed into an oscillating conveyor, which is then indexed forward and used to transfer the raw materials into the melt furnace. Electric induction furnaces are used to melt the metal. Once the melt cycle is complete, the molten metal is poured into a transfer ladle. The molten metal is then poured into a large electric furnace, where it is held until required by the molds.